The third building block is the irrotational vortex, which we discussed earlier when we were looking at the meaning of vorticity and rotationality. And so, building block number 3, and that's called the irrotational vortex. And from kind of what we understand about this vortex, it has just a tangential velocity, okay, bunch of u thetas over here, u theta, and you can derive this in different ways. Either start with the vorticity, definition of vorticity, and pick up a, so for example, do omega z, that's equal to 1 over r, d by dr of r u theta minus dur by d theta. You want that equal to 0, so this is ur is not 0, ur is equal to 0 and u theta is not 0. So what is u theta such that this returns in irrotational flow? You can do it this way. Set this guy is equal to 0. So this gives us d by dr of r u theta equal to 0. And therefore you want r u theta to be a constant. So this implies that r u theta is equal to some constant, and u theta is equal to k over r. So that gives you the definition of the irrotational vortex. Another argument would be actually to do some other integration of the circulation, and then you get actually the value of k, which is the strength of the vortex or the circulation, what we call gamma over 2 pi. But anyway, it's just a constant over r. And in this case, ur is equal to d phi by dr is equal to 0, and that's equal to 1 over r d psi by d theta, again in polar coordinates. And u theta is k over r, and that's equal to 1 over r d phi by d theta, and equal to d psi by dr. Doing the integration, you can immediately find that phi is equal to k times theta. So what this does, it swaps the source and sink. So now phi is lines of constant theta, and psi are lines of constant r, okay, or log r. Okay, so what this did, it swapped the streamlines, the stream function, and the velocity potential with the source, right? So now the streamlines are these concentric lines, they're rotating, and the velocity potential are lines of constant theta. And we can also move vortex at point A, B. Similarly, we get phi is equal k to k theta 1. Look at my previous video, which is equal k inverse tan y minus b over x minus a. And psi is k log minus k log r1. That's equal to minus k log square root of x minus a squared plus y minus b squared. So to remind you of this configuration, we're gonna put the vortex at some point A, B, which is not at the origin. This is point A, B. And at a point P, r theta or xy, okay, this would be position vector r, angle theta, then you can reconstruct the flow. Everything is done with respect to the point AB, so this would be R1 and this would be theta 1. So the entire flow is defined with respect to the irrotational vortex over here. Okay, and then you do everything relative to that point, and you can obtain this solution. You can plot it and manipulate x and y however you like. If you use polar coordinates, then x is r cosine theta and y is equal to r sine theta, etc. And then you can plot your solution however you like.